I'm going to ask you something most science educators won't. What does it feel like to not know? Not the comfortable, I'll Google it later kind of not knowing. The deep kind. The kind that physicists face when they admit their most successful theory in history contains its own destruction. Every equation about spacetime comes with a warning label. Past this point, I cannot help you. We've sent humans to the moon using these equations. We've photographed the edge of black holes with them. And yet the theory itself says, here's where I fail: at the beginning of time, at the end of matter, at the smallest possible scales. This isn't about what we haven't discovered yet. This is about our best answers, pointing to their own limitations. Tonight, we're not going to pretend that's okay. We're going to sit with that discomfort and ask, what does it mean that the foundation of reality has a question mark at its core? Because here's what I've learned after a lifetime of exploring the natural world. The most honest thing any of us can say is, I don't know, but I'm looking. And spacetime, this idea that sounds so fundamental, so solved, so settled, is perhaps the greatest I don't know in all of science. Now, before we go any further, I need to tell you why this video matters. Why you should spend the next 2 hours with me exploring something that might seem abstract or distant from your daily life. Because it's not. It's not distant at all. You've been lied to, not maliciously, but by omission. Every science class you've ever taken, every documentary you've watched, every article about Einstein you've read has made it sound like we understand spacetime. We don't. We have equations that work brilliantly. We lack comprehension of what those equations actually describe. And that gap isn't a footnote in a physics textbook. It's the central mystery of our time. Let me be direct with you. Most people think spacetime is solved science. Something Einstein figured out in 1915, something we've moved past, something that's just background information now. The truth is far more unsettling and far more exciting. Spacetime is something we use without understanding. It's like a civilization that discovered electricity and built entire cities powered by it, but didn't know what electrons were, didn't know about atoms, didn't know about quantum mechanics. They could flip switches and lights would come on, but if you asked them, what is electricity really? They'd have equations for how it flows through wires and no idea what's actually flowing. That's where we are with spacetime. Your phone needed it to tell you where you were this morning. The GPS satellites orbiting above us right now are programmed to account for time dilation, the fact that clocks in orbit farther from Earth's gravitational pull run faster than clocks on the ground. Not metaphorically faster, actually faster by about 38 microseconds per day. Engineers discovered this not through philosophy, but through measurement. They launched atomic clocks into space and compared them to identical clocks on Earth, and the ones in space ticked faster. If GPS didn't correct for this, your navigation would be wrong by miles within hours. This isn't theoretical physics. This is measured reality. Time itself runs at different rates depending on where you are in a gravitational field. And yet, ask any physicist, any honest physicist, what time actually is, and they'll tell you, we don't know. We can measure it. We can predict how it behaves. We cannot explain what it is. So here's what this video is going to give you. First, intellectual honesty. I'm going to be clear about what we know. Spacetime curves around massive objects. It propagates waves at the speed of light. It dilates when you move fast or fall into gravity. And what we don't know, which is its fundamental nature, its composition, whether it's even a real thing or an emergent property of something deeper. Second, emotional relief. You're going to stop feeling like you're supposed to get spacetime in some complete way, because even the people who work with it every day don't get it completely. And there's beauty in that. There's freedom in admitting the limits of our knowledge. Third, a reframe of mystery itself. In our culture, mystery is treated as something to eliminate, something uncomfortable, something that means we've failed. I want to show you that mystery is an invitation. It's not a wall, it's a door. And here's the unique insight, the thing that makes this different from every other physics video you've watched. The biggest discovery in physics over the past 50 years isn't a new particle or a new force or even a new phenomenon. It's a growing realization that space and time might be emergent. They might not be fundamental building blocks of reality at all. They might arise from something deeper, something more basic, the way temperature arises from the motion of molecules. Temperature isn't a thing in itself, it's a statistical property describing how fast particles are moving. You can't have temperature without particles. And increasingly, the evidence suggests that you can't have space and time without quantum entanglement, without information, without patterns we're only beginning to understand. This means everything you think of as real, the distance between you and the stars, the duration between now and tomorrow, the gap between your hand and this screen, might be a kind of illusion, not fake, but derived, secondary, a way your brain makes sense of something more fundamental that you can't perceive directly. And that changes everything. It changes physics, obviously, but it also changes philosophy. It changes what we mean when we say something exists. It changes how we think about the beginning of the universe and the possibility of other universes. It changes whether time travel might be possible, whether wormholes could exist, whether reality is anything like what it appears to be. So unlike typical physics content that either dumbs things down until they're meaningless or drowns you in mathematics you can't follow, this video is going to treat you as someone capable of sitting with uncertainty. We're going to explore 3 genuine mysteries, 3 places where physics breaks down and the equations start giving nonsensical answers. What is space-time made of? What happened at the Big Bang singularity? Do black holes destroy information? These aren't rhetorical questions with neat answers waiting at the end. They're open wounds in physics. They're places where the map has blank spaces marked, "Here be dragons." And understanding why they matter to technology, to philosophy, to what it means to be a conscious creature in a mysterious cosmos that's more valuable than false certainty. By the end of tonight, you won't just know about space-time's mysteries. You'll feel them. You'll understand why physicists lose sleep over whether information can be destroyed and what happens at the Planck length. You'll see how the same theory that powers your phone also predicts places where it stops working. And you'll walk away with something rare in our age of instant answers. Comfort in not knowing. Not because ignorance is bliss, but because you'll finally grasp what the real questions are. And knowing what to ask is the first step toward wisdom. So let's begin. Let's start not with equations or abstractions, but with people, with stories. Because space-time isn't just an idea, it's woven into human history, into moments of revelation and struggle, into the fabric of how we came to see the universe differently. There's a young man I want you to imagine, 26 years old. It's 1905. He works in Bern, Switzerland, in a patent office. His job is to examine applications for electromagnetic devices, motors, dynamos, things people are inventing as electricity transforms the world. He's not a professor. He doesn't work at a university. He has no laboratory, no team, no resources. During the day, he reads patent applications and writes reports. At night, and during stolen moments at his desk, he thinks about light. His name is Albert Einstein, though nobody knows that name yet. Nobody outside his small circle of friends has heard of him. He has a degree in physics, but it didn't lead anywhere. He applied for academic positions and was rejected. He applied to be a high school teacher and was turned down. So he took a civil service job examining patents, and it was there, in that small office, working in obscurity, that he started to dismantle 300 years of physics. He'd become obsessed with a question that seemed simple but was actually impossible. What would you see if you could ride alongside a beam of light? If you were traveling at the speed of light yourself, right next to a light wave, what would it look like? Would the wave appear frozen, stationary beside you, the way a car on the highway seems motionless when you're driving the same speed? According to the physics of his time, yes, light should appear frozen if you're moving at light speed. But according to Maxwell's equations, the equations describing electricity and magnetism, light always moves at the same speed, always. There's no reference frame where light stands still. And this created an impossible contradiction. 2 sets of equations, both experimentally verified, both successful, saying opposite things. Einstein realized that something fundamental had to give. And what gave was time itself. He published a paper that year, one of 4 extraordinary papers he wrote in 1905 while working full-time at the patent office. The paper was called On the Electrodynamics of Moving Bodies, though history would know it as special relativity. And its core insight was radical. The speed of light is absolute. It's the same for everyone, no matter how fast they're moving. What adjusts, what flexes, what changes to keep light speed constant is space and time themselves. If you're moving very fast relative to someone else, time literally runs slower for you from their perspective. Not because your clock is broken, because time itself is different. And distances in the direction you're moving actually contract, they shrink. These aren't optical illusions, they're real physical effects, measured thousands of times since. Think about what this really means. Imagine you could build a spaceship that travels at 99% of the speed of light. You take a journey to a star 10 light years away and back. From your perspective on the ship, the journey might only take a couple of years. Your clock, your heartbeat, your aging, everything happens normally for you. But when you return to Earth, 20 years have passed. Your friends have aged 20 years. Your children, if you had any, might now be older than you. This isn't science fiction. This is what Einstein's equations predict, and particle accelerators confirm it every day. Unstable particles that normally decay in microseconds live much longer when they're traveling at 99.9% of light speed. We've put atomic clocks on airplanes and flown them around the world. And when we brought them back and compared them to identical clocks that stayed on the ground, the traveling clocks showed less time had passed. Just a few hundred nanoseconds, but it matched Einstein's predictions exactly. The implications are staggering. There's no universal now, no cosmic clock ticking at the same rate everywhere. When you say something is happening right now on a distant planet, that statement has no absolute meaning. Different observers moving at different speeds would disagree about what right now means. They disagree about which events are simultaneous. Time is not a river flowing at a constant rate for everyone. It's more like a fabric that can stretch and compress depending on how you're moving through it. But Einstein wasn't done. Special relativity only dealt with objects moving at constant speeds. It didn't handle acceleration, it didn't handle gravity, and gravity was a problem. Newton's law of gravity had worked brilliantly for over 200 years. You could use it to predict the motion of planets with extraordinary precision, calculate the trajectory of cannonballs, understand the orbits of moons. It was one of the most successful theories in the history of science. But Einstein realized it couldn't be completely right. Newton's gravity worked instantly. If the sun suddenly disappeared, Earth would immediately fly off into space. According to Newton's equations, the gravitational pull would vanish instantly across 93 million miles of empty space. But Einstein had just shown that nothing can travel faster than light. No signal, no force, no information can cross space instantaneously. If the sun disappeared, it would take about 8 minutes for us to stop seeing it. That's how long light takes to travel from the sun to Earth. And Einstein realized gravity couldn't work any faster than light either. There had to be a delay. Something had to carry the gravitational force, and whatever it was couldn't move faster than light. This led Einstein to what he later called the happiest thought of his life. It came to him in 1907. He was sitting in his office at the patent office, still thinking about gravity, when he imagined a worker falling off a roof. And he realized something profound. While the worker is falling, they don't feel their own weight. They're weightless. They're in free fall. If they dropped a hammer while falling, the hammer would just float next to them, falling at the same rate. From the worker's perspective, the hammer wouldn't accelerate toward the ground or away from them, it would hover there in midair. This seems obvious now. We've all seen footage of astronauts floating in the International Space Station, but Einstein realized something deeper. The worker falling off the roof and the astronaut floating in space are experiencing the same thing. They're both in free fall. The astronaut isn't floating in zero gravity. They're falling toward Earth, but they're also moving sideways fast enough that they keep missing Earth. That's what an orbit is, continuously falling, but continuously missing the ground. And that's why astronauts feel weightless. Not because there's no gravity, but because they're in free fall. Einstein realized that being in freefall is indistinguishable from being in empty space with no gravity at all. And being in a rocket accelerating upward is indistinguishable from standing on the surface of a planet, feeling gravity pull you down. You can't tell the difference. If you're in a closed room with no windows, there's no experiment you can do to determine whether you're sitting on Earth's surface or sitting in a rocket in deep space accelerating upward. The effects are identical. This is called the equivalence principle. Acceleration and gravity are equivalent. They're the same thing, and this was the key. If acceleration and gravity are the same thing, and if special relativity says acceleration affects space and time, then gravity must also affect space and time. Gravity must curve space and time. It took Einstein 8 more years to work out the mathematics. From 1907 to 1915, he struggled. He learned tensor calculus, a branch of mathematics he'd never studied, from his friend Marcel Grossmann. He made mistakes. He published wrong results, then had to retract them. He tried different formulations, different approaches. It was the hardest work of his life. He later said the final year, from late 1914 to November 1915, was the most exhausting and demanding time of his entire career. But in November 1915, he got it right. He published the field equations of general relativity, and physics would never be the same. General relativity says that mass and energy curve space-time, and objects moving through curved space-time follow curved paths. That's what we experience as gravity. It's not a force pulling objects together. It's objects following the straightest possible paths through warped geometry. Those paths just happen to curve because the geometry itself is curved. The classic analogy is a rubber sheet. Imagine stretching a flat rubber sheet taut. If you place a heavy ball in the middle, it creates a dip. Now, if you roll a smaller ball across the sheet, it curves toward the heavy ball, not because the heavy ball is pulling it, but because the sheet itself is curved. The small ball is trying to roll in a straight line, but the curved sheet forces it to follow a curved path. This is what mass does to space-time. The sun curves space-time around it. Earth is trying to move in a straight line through space, but the curved space-time around the sun forces Earth to follow a curved path. That curved path is Earth's orbit. We experience this as the sun's gravity pulling on Earth, but from Einstein's perspective, there's no pull at all. Earth is just moving through curved space-time, following a geodesic, the straightest possible path through the curved geometry. Now, this rubber sheet analogy is helpful, but it's also misleading. The rubber sheet is a two-dimensional surface curving in three-dimensional space. But space-time is four-dimensional, 3 dimensions of space plus 1 of time, and it's not curving in some higher dimensional space. It's curving in on itself. This is hard to visualize because our brains didn't evolve to understand 4-dimensional geometry. Einstein struggled for years to find the right mathematical language. The field equations he finally published are beautiful in their symmetry, but solving them for realistic situations is extraordinarily difficult. They're nonlinear, partial differential equations. The curvature affects how mass and energy behave, but mass and energy also affect the curvature, creating feedback loops that make the equations brutally hard to solve. Even today, solving Einstein's equations for something like 2 black holes colliding requires massive supercomputers running for months. One of the first successes was explaining the orbit of Mercury. Mercury's orbit had a peculiarity that astronomers had known about for decades but couldn't explain. The point where Mercury is closest to the Sun shifts very slightly with each orbit. This is called the precession of Mercury's perihelion. Some astronomers thought there might be another planet closer to the Sun than Mercury pulling on it. But Einstein's equations predicted the exact amount of precession without needing any extra planets. Space-time was simply curved more strongly near the Sun, and that extra curvature explained Mercury's strange orbit perfectly. But the real test came in 1919. Einstein's theory predicted that light would be bent by gravity. Starlight passing near the Sun would be bent by the Sun's curved space-time, making stars appear to shift position slightly when the Sun was nearby. But you can't normally see stars near the sun. The sun is too bright. You can only see them during a total solar eclipse. On May 29th, 1919, there was a total solar eclipse. Two expeditions, one to the island of Principe off the coast of West Africa, led by Arthur Eddington, and another to Brazil, photographed stars during the eclipse. They measured the positions of stars near the sun and compared them to the positions of those same stars photographed at night when the sun wasn't nearby. The stars had shifted. Light had been bent by the sun's gravity, exactly as Einstein predicted. When the results were announced in November 1919, Einstein became an overnight celebrity. Newspapers around the world ran headlines. His face appeared on magazine covers. He went from being a respected physicist to being the most famous scientist in the world. The man who had worked in obscurity in a patent office was now lecturing to packed halls everywhere. By 1922, everyone in physics agreed Einstein had solved gravity. The problem was closed. The theory was complete. Except it wasn't. Einstein's equations were beautiful, but they were also difficult. Most physicists couldn't solve them, except in very simple cases. One of the simplest solutions was found by Carl Schwarzschild in 1916, just months after Einstein published his theory. Schwarzschild was a German physicist serving in the German army during World War I. Despite being on the Russian front, dealing with harsh conditions and warfare, he found time to work on Einstein's equations. He solved them for the simplest possible case: a perfectly spherical, non-rotating mass sitting alone in empty space. The solution worked. It described how space-time curves around a star or planet. But Schwarzschild noticed something strange in the mathematics. At a certain distance from the center of the mass, the equations seemed to break. They gave infinite values. They stopped making sense. This distance became known as the Schwarzschild radius. For the Sun, it's about 3 kilometers. For Earth, it's about 9 millimeters. These numbers seemed meaningless at the time because the Sun is much larger than 3 kilometers across it, has a radius of about 700,000 kilometers. Earth is much larger than 9 millimeters. The strange behavior in the equations only appeared deep inside the physical mass, where the vacuum solution didn't really apply anyway. So most physicists ignored it. It was just a mathematical quirk, an artifact of the idealized solution. Nothing to worry about. Schwarzschild himself died just a few months after publishing his solution. He contracted an autoimmune disease while serving on the Eastern Front and died in May 1916 at the age of 42. He never knew how important his solution would become. For decades, the Schwarzschild radius remained a mathematical curiosity. If you somehow compressed a mass smaller than its Schwarzschild radius, the equations predicted something bizarre. Space-time would curve so strongly that nothing could escape, not even light. The object would become what we now call a black hole. And at the very center, all the mass would collapse to an infinitely small point, a singularity where the curvature of space-time became infinite and the laws of physics broke down completely. Einstein thought this was absurd. He believed it revealed a limitation of the theory, not a prediction about reality. He wrote papers in the 1930s arguing that nature would never allow such a thing. He believed matter would resist being compressed that much. There'd be some force, some pressure, some quantum effect that would prevent collapse beyond the Schwarzschild radius. The singularity was like dividing by zero in an equation. You get infinity, but that doesn't mean infinity exists in nature. It means you've pushed the equation beyond where it's valid. Most physicists agreed with Einstein. The idea of a star collapsing so completely that it disappeared from the universe seemed ridiculous. Stars are held up by pressure. Hot gas pushes outward, balancing gravity's inward pull. When a star runs out of fuel, it cools down, pressure drops, and gravity takes over. But surely something would stop the collapse. Maybe electron degeneracy pressure, which holds up white dwarf stars. Maybe neutron pressure, which holds up neutron stars. Something would stop it, it had to. But in 1939, Robert Oppenheimer, who would later lead the Manhattan Project, and his student Hartland Snyder, published a paper that changed everything. They modeled a massive star running out of fuel, no longer able to support itself against its own gravity. and they showed mathematically that nothing could stop the collapse. No pressure, no force was strong enough to halt it once it started. The star would shrink past its Schwarzschild radius and keep shrinking until it became a singularity, a point of infinite density where Einstein's equations themselves broke down. Oppenheimer and Snyder didn't call it a black hole. That term wouldn't be coined until 1967 by John Wheeler. They just described the mathematics of gravitational collapse. But the implications were clear. Einstein's own equations predicted that stars could collapse into objects from which not even light could escape. Objects where space-time became so warped that it essentially sealed itself off from the rest of the universe. Einstein hated this result. He thought it showed general relativity must be incomplete, that something was missing. But he couldn't find a flaw in Oppenheimer's mathematics. The equations were correct. General relativity really did predict these objects. Einstein died in 1955, never accepting that black holes were real. For the next couple of decades, most physicists remained skeptical. Black holes seemed too strange, too extreme. But observations started piling up. In the 1960s, astronomers discovered quasars, incredibly bright objects in distant galaxies, pouring out enormous amounts of energy from very small regions of space. The only explanation that made sense was supermassive black holes, millions or billions of times the mass of the Sun, feeding on gas and dust. And theorists were making progress understanding what black holes meant for physics. In 1965, Roger Penrose proved a remarkable theorem. Once a star collapses past a certain point, the formation of a singularity is mathematically unavoidable. It's not a matter of the star being perfectly spherical or having special properties. Any collapsing star forms a singularity. The laws of physics, as described by general relativity, literally force it to happen. Stephen Hawking extended this work. In the late 60s and early 70s, working with Penrose and others, he proved that singularities are generic features of general relativity. They don't just appear in black holes. The Big Bang itself was a singularity, a point of infinite density and infinite curvature where time itself began. This was deeply troubling. General relativity had been incredibly successful. It had never failed a test. But the theory itself predicted places where it broke down, where the equations gave infinite answers and stopped making sense. Singularities were like signs posted in the mathematics saying, beyond this point, physics doesn't work. Then in 1974, Hawking made another discovery that shocked everyone. He showed that black holes aren't completely black. They emit radiation. This became known as Hawking radiation, and it came from combining general relativity with quantum mechanics. Here's how it works. Quantum mechanics says empty space isn't really empty. It's filled with quantum fluctuations, pairs of particles and antiparticles that pop into existence for incredibly brief moments before annihilating each other. This happens everywhere, all the time. Usually, these virtual particles appear and disappear so quickly that they have no observable effect. But near the event horizon of a black hole, something different can happen. Imagine a virtual particle pair appearing right at the edge of the event horizon. One particle appears just inside the horizon, the other just outside. Normally they'd annihilate each other almost instantly. But in this case, the particle inside the horizon gets pulled in by the black hole's gravity before it can annihilate its partner. The particle outside escapes. To an outside observer, it looks like the black hole emitted a particle. Where did the energy for this real particle come from? It came from the black hole itself. The particle falling in has negative energy from the perspective of an outside observer, a strange consequence of general relativity near a black hole. It reduces the black hole's mass very slightly. The escaping particle carries away positive energy. Total energy is conserved, but the black hole has lost mass. Over time, this process causes the black hole to evaporate. The rate depends on size. Smaller black holes evaporate faster. A black hole with the mass of the Sun would have a temperature of about 60 nanokelvin, 60 billionths of a degree above absolute zero. At that temperature, it would take about 10 to the 67 years to evaporate completely. That's incomprehensibly long. The current age of the universe is only about 14 billion years, but a smaller black hole would evaporate much faster. This was revolutionary. It meant black holes aren't eternal, they have a finite lifetime. They eventually disappear completely, evaporating away into radiation. And this created a new problem, one that has haunted physics for 50 years. It's called the information paradox. Think about it like this. Imagine you write a book and throw it into a black hole. The book contains information, the arrangement of words, the positions of atoms. It crosses the event horizon and falls toward the singularity. From the outside, the black hole gained a tiny bit of mass, but you can't tell what fell in. A book, a rock, a star, the black hole looks the same. In the 1970s, John Wheeler summarized this by saying, black holes have no hair, meaning they have no features that distinguish what went into them. If black holes were eternal, you might say the information is locked inside forever, inaccessible but not destroyed. But Hawking radiation changes that. The black hole evaporates and eventually disappears, replaced by a cloud of thermal radiation. Thermal radiation is random. It doesn't carry information about what created it. This means the information about the book is destroyed. The words, the ideas, the specific arrangement of particles, all gone. This violates a fundamental principle of quantum mechanics called unitarity. Quantum mechanics says information is never destroyed. It can be scrambled, spread out, hidden in complex ways, but it's always there in principle. But Hawking radiation seemed to destroy information. This created a deep conflict between general relativity and quantum mechanics. One of them had to be wrong, or both had to be incomplete. Physicists debated this for decades. Hawking initially argued that information really is destroyed, that quantum mechanics breaks down in extreme gravitational fields. Others argued that information must be preserved somehow, that we just don't understand the mechanism yet. The paradox remained unsolved, and it became a signal that something was fundamentally wrong with our understanding of space-time. Now, before we go deeper into these mysteries, I want you to pause and appreciate something remarkable. This idea we don't fully understand, this theory that breaks down at singularities and might destroy information, is something we use every single day. Your phone this morning told you where you were because GPS satellites account for general relativity. The satellites orbit at about 20,000 kilometers up. At that altitude, they're moving at about 14,000 kilometers per hour relative to the ground. According to special relativity, time should run slower for moving objects. The satellite clocks should lose about 7 microseconds per day compared to clocks on the ground. But there's a second effect that's even larger. The satellites are higher up in Earth's gravitational field. They experience weaker gravity. According to general relativity, time runs faster in weaker gravitational fields. The satellite clocks gain about 45 microseconds per day. Add these effects together, and the satellite clocks run about 38 microseconds per day faster than clocks on the ground. That might not sound like much, but light travels about 300 meters in 1 microsecond. If GPS didn't correct for these relativistic effects, your position would be off by about 11 kilometers per day. Within hours, GPS would be completely useless. The engineers who designed GPS knew this. They programmed the satellite clocks to tick at a slightly different rate to compensate. Every GPS calculation accounts for the curvature of space-time around Earth. Every time you use GPS, you're relying on Einstein's equations. And it works. It works perfectly. But do we understand what space-time actually is? No, we don't. We just know how to calculate its effects. Here's another example that's even stranger. The color of gold. Gold has a distinctive yellow color. It's the only metal that looks yellow. Silver is silvery white. Copper is reddish. But gold is yellow. Why? The answer involves relativity. Gold atoms have 79 protons in the nucleus, creating a strong electric field. The innermost electrons are moving very fast in this field, fast enough that relativistic effects become important. According to special relativity, as electrons move faster, their effective mass increases. This changes the spacing between energy levels in the atom. For gold, this relativistic effect shifts the energy levels enough that gold absorbs blue light instead of ultraviolet. When white light hits gold, blue frequencies are absorbed. The remaining light that's reflected is yellow. The color of gold is a relativistic effect. Without special relativity, gold would look silvery like most other metals. The same thing happens with mercury. Mercury is the only metal that's liquid at room temperature. Why? Again, relativity. Mercury atoms have 80 protons, and the innermost electrons are moving so fast that relativistic effects make the bonds between mercury atoms weaker than they'd otherwise be. The atoms don't stick together as strongly, so mercury melts at a much lower temperature than you'd expect. These aren't just curiosities. These are real, measurable effects in everyday materials. The universe we live in is shaped by relativity. Or think about LIGO, the gravitational wave detector. LIGO is designed to detect ripples in spacetime caused by violent cosmic events like colliding black holes. These ripples stretch and squeeze space as they pass through. The effect is incredibly small. When a gravitational wave passes through Earth, it might change the distance between 2 points separated by 4 kilometers by less than 1/10,000th the width of a proton. Let me put that in perspective. A proton is about 10 to the minus 15 meters across. 1/10,000th of that is 10 to the minus 19 meters. LIGO can measure changes that small. The first detection happened on September 14th, 2015. It was the first day of LIGO's first science run after a major upgrade. The signal arrived at the detector in Louisiana at 5:51 a.m. 7 milliseconds later, it arrived at the detector in Washington state. The signal lasted about 1/5 of a second, starting at a frequency of about 35 Hertz and rising to about 250 Hertz before cutting off. This pattern is exactly what you'd expect from two black holes spiraling into each other and merging. The analysis showed that black holes each had about 30 times the mass of the Sun. They'd been orbiting each other for billions of years, gradually spiraling inward. In the final fraction of a second, they were orbiting each other hundreds of times per second, moving at significant fractions of the speed of light. When they merged, the collision released more energy in a fraction of a second than all the stars in the observable universe emit in the same time. About 3 solar masses worth of energy was radiated away as gravitational waves. That energy radiated outward as ripples in space-time. The event happened 1.3 billion light-years away, so the waves took 1.3 billion years to reach Earth. When they arrived, they stretched and squeezed the 4-kilometer arms of LIGO by about 1,000th the width of a proton, and LIGO detected it. Since then, LIGO and its sister observatories have detected dozens of gravitational wave events. Each one is direct evidence that space-time is real, that it can be bent and rippled, that Einstein was right. We're not inferring the existence of space-time from theory. We're measuring it directly. We're watching it wiggle. But detecting gravitational waves doesn't tell us what space-time is made of. It just confirms it exists and behaves the way Einstein's equations say it should. It's like detecting sound waves traveling through air. You can measure the waves, study their properties, use them to communicate, but measuring sound waves doesn't tell you what air is made of. You need other experiments to discover molecules and atoms. Similarly, measuring gravitational waves tells us space-time can vibrate. It doesn't tell us what the fabric doing the vibrating actually is. And then there are the black hole photographs. In April 2019, the Event Horizon Telescope collaboration released the first image of a black hole. It wasn't a photograph in the traditional sense. It was radio telescope data from observatories all around the world, combined using very long baseline interferometry. 8 radio telescopes spread across the planet from Hawaii to Antarctica, from Spain to Chile, all pointed at the same target. They recorded radio waves at a wavelength of 1.3 millimeters, a frequency where the gas around black holes glows brightly. By combining signals from telescopes across the planet, you can achieve a resolution equivalent to a telescope the size of Earth, about 13,000 kilometers across. That's enough resolution to see an orange sitting on the surface of the moon. The result was an image showing a ring of light around a dark circle. The black hole was in the center of the galaxy, Messier 87, about 55 million light-years away. The black hole is about 6.5 billion times the mass of the Sun. The dark region in the center, the shadow, has a diameter of about 40 billion kilometers. That's about 3 times the size of Pluto's orbit. It's completely dark because it's the event horizon. No light escapes from inside. The ring of light around the shadow is gas orbiting the black hole at speeds approaching the speed of light, heated to billions of degrees. What you're seeing in that image is light being bent by the extreme curvature of space-time. Some photons orbit the black hole multiple times before escaping. The image is a direct photograph of Einstein's predictions made visible. In May 2022, they released an image of a second black hole, the one at the center of our own galaxy, Sagittarius A star, about 4 million times the mass of the Sun, much closer at about 27,000 light-years away. Again, the image shows a ring of light around darkness. You're looking at curved space-time. You're seeing photons bent by gravity. We use this idea every day in GPS, in the color of gold, in gravitational wave detectors, in photographs of black holes. We've built entire technologies on Einstein's framework, and that's both amazing and unsettling. It's like discovering your house rests on an invisible foundation. You can measure how it responds to weight. You can calculate how it bends. You can predict how it behaves, but the material itself remains unknown. So let's dig into the mystery. Let's be clear about what we don't understand. There are 3 big questions, 3 places where our knowledge hits a wall, 3 puzzles that, if we could solve them, would revolutionize physics. The first question: what is space-time made of? Einstein's equations describe how space-time curves in response to mass and energy. They tell us how to calculate the curvature. They predict how objects move through curved space-time. But they don't tell us what space-time actually is. In Einstein's theory, space-time is treated as a smooth continuum. You can zoom in on any point, and there's always more space at smaller scales. You can divide time into smaller and smaller intervals, and there's always more time. Space and time are continuous, infinitely divisible. This works perfectly for calculations. But there's reason to believe it can't be the whole story. Quantum mechanics says almost everything in nature is discrete, quantized. Energy comes in chunks, light comes in chunks, even electron spin comes in discrete values. The quantum world is fundamentally grainy, not smooth. This suggests space and time might also be quantized at very small scales. There might be a smallest possible length, a quantum of space. There might be a smallest possible duration, a quantum of time. This scale is called the Planck length. It's about 10 to the minus 35 meters. To give you a sense of how small this is, a proton is about 10 to the minus 15 meters across. The Planck length is 20 orders of magnitude smaller than a proton. If you scaled a proton up to the size of the observable universe, the Planck length would be about the size of a tree. At this scale, quantum effects on space-time itself should become important. The smooth fabric Einstein described should break down into something else, something grainy, something chaotic. Physicists call this quantum foam. If you could zoom in far enough, space-time would look turbulent, bubbling with quantum fluctuations. But we have no direct way to probe these scales. The Planck length is so small we can't build experiments to measure it. The energies required would be about 10 to the 19 giga-electron volts. The Large Hadron Collider reaches energies of about 14,000 giga-electron volts. To probe the Planck scale, you'd need an accelerator about 10,000 trillion times more powerful. So we're stuck trying to figure out what happens at these scales using pure theory. One leading candidate is loop quantum gravity. This approach tries to quantize Einstein's equations directly. Instead of treating space-time as smooth, loop quantum gravity says space-time is made of discrete chunks connected in a network. Space is woven from loops about a Planck length in size. These loops connect to form a network, and geometry emerges from how they're arranged. In this picture, area and volume are quantized. You can't have an arbitrary area, they come in discrete units. Space-time has a minimum possible volume. You can't divide it smaller. This solves some problems. It suggests singularities might not actually exist. Instead of collapsing to an infinitely small point, matter would collapse to a minimum volume set by quantum effects. The singularity would be replaced by a quantum bounce. But loop quantum gravity has problems. It's mathematically very complex. It's hard to extract testable predictions, and it hasn't been successfully unified with the other forces of nature. Another approach is string theory. String theory says fundamental objects aren't point particles but tiny vibrating strings. Different vibrations correspond to different particles. An electron is one vibration, a photon is another, and one vibration corresponds to the graviton, the quantum particle carrying gravity. In string theory, space-time emerges from the interactions of these strings. The strings exist in a higher dimensional space, usually 10 or 11 dimensions. The extra dimensions are curled up so small we don't notice them. And the geometry of space-time comes from how strings move and interact. String theory is elegant. It naturally includes gravity, it unifies all forces, it has a rich mathematical structure, but it also has serious problems. We've searched for supersymmetry, a key prediction, and haven't found it. And there are about 10 to the 500 possible versions of string theory, depending on how you curl up the extra dimensions. This is called the landscape problem. With 10 to the 500 possibilities, how do we know which describes our universe? Some physicists argue maybe all these vacua are real, each describes a different universe in a vast multiverse. Our universe is one particular point in this landscape. This anthropic reasoning troubles many physicists. It seems to give up on explaining why the laws have the specific form they do. And string theory makes almost no testable predictions at energies we can reach. The natural scale is the Planck energy. To probe that directly, we'd need an accelerator 10,000 trillion times more powerful than the LHC. There's also a more radical idea gaining traction. Maybe space-time isn't fundamental at all. Maybe space and time are emergent properties arising from something deeper. This is the idea behind ER equals EPR. In 1935, Einstein and colleagues wrote about quantum entanglement. Two particles correlated, such that measuring one instantly affects the other, no matter how far apart. Also in 1935, Einstein and Nathan Rosen wrote about wormholes, shortcuts through space-time connecting distant regions. In recent years, physicists have wondered if there's a connection. The equation ER equals EPR suggests that when two particles are entangled, they're connected by a tiny wormhole. If this is true, space-time itself would be woven from entanglement. The geometry we think of as space-time would emerge from quantum correlations. Space would be an illusion, a useful way of describing something more fundamental. Distance would emerge from the pattern of entanglement. This is speculative, but it points to a possibility both exciting and unsettling. Everything we think we know about space and time might be wrong at a fundamental level. They might not be basic building blocks. They might be emergent, appearing only at large scales, like how temperature emerges from molecular motion. The bottom line, we don't know what space-time is made of. We have equations describing its behavior, we can measure its curvature, we can detect waves moving through it, but the fundamental nature of the fabric itself remains a mystery. The second question, what happened at the Big Bang? When we run the universe's expansion backward using Einstein's equations, we reach a point where the entire universe was compressed into an infinitely small, infinitely dense singularity. This is called the Big Bang singularity. But calling it a singularity is another way of saying the equations break down, density becomes infinite, temperature becomes infinite, the curvature becomes infinite, the mathematics stops working. We have very good evidence for the Big Bang in a general sense. The universe is expanding, we can measure it. We can see galaxies moving away from us. The farther away a galaxy is, the faster it's receding. This relationship was discovered by Edwin Hubble in 1929. If the universe is expanding now, it must have been smaller in the past. Run the clock backward and everything gets closer together. Temperatures and densities increase. Eventually, about 13.8 billion years ago, the universe was incredibly hot and dense. We have other evidence. In 1964, Arno Penzias and Robert Wilson discovered the cosmic microwave background. They were at Bell Labs using a horn antenna for satellite communications. They kept detecting background noise that wouldn't go away, no matter which direction they pointed the antenna. Finally, they learned that physicists at Princeton had predicted exactly such a signal. If the universe started hot and dense and then expanded and cooled, there should be leftover radiation from that early phase. The radiation would have been stretched by cosmic expansion from high-energy gamma rays down to microwave frequencies. Penzias and Wilson had accidentally discovered proof of the Big Bang. The cosmic microwave background is light left over from when the universe was about 390,000 years old. Before that, the universe was so hot that atoms couldn't form. It was opaque plasma. Light couldn't travel far. Photons constantly scattered off free electrons. But as the universe expanded and cooled, electrons and protons combined to form hydrogen atoms. Suddenly, light could travel freely. The universe became transparent. Those photons have been traveling ever since, stretched by cosmic expansion from visible light to microwave radiation. We can detect this radiation today from every direction. It's nearly uniform, with a temperature of about 2.7 Kelvin. But it's not perfectly uniform. There are tiny variations, about 1 part in 100,000. These variations are the seeds of structure. Regions that were slightly denser had slightly higher temperatures. These regions had slightly stronger gravity. Over billions of years, matter was pulled into these denser regions. The tiny variations grew into galaxies, galaxy clusters, and superclusters. Every galaxy, every star, every planet exists because of tiny quantum fluctuations in the early universe. We've mapped these temperature variations with satellites. The Planck satellite produced the most detailed map yet. From these maps, we can determine fundamental properties: the universe's age, its composition, its geometry, the rate of expansion. Modern cosmology can explain the patterns we see to better than 1% precision. But when we try to understand the very beginning, we run into problems. Einstein's equations predict a singularity. But singularities are places where the theory breaks down. At the Planck time, about 10 to the minus 43 seconds after the Big Bang, quantum effects on spacetime should become important. Below this timescale, general relativity can't be trusted. We need a quantum theory of gravity, and we don't have one. The best we can do is patch the problem with cosmic inflation. Inflation was proposed in the early 80s. The idea is that in the very early universe, space expanded exponentially fast. In a tiny fraction of a second, the universe grew by a factor of at least 10 to the 26. This solves several problems. It explains why the universe looks uniform. Regions now separated were once close enough to interact. It explains why space appears flat. And it explains structure quantum fluctuations during inflation were stretched to cosmic scales. Inflation is supported by observations. The patterns in the cosmic microwave background match predictions. But inflation doesn't solve the singularity problem. It just pushes it back. Inflation requires specific initial conditions. Where did those come from? We don't know. Some physicists propose alternatives. Maybe the Big Bang wasn't the beginning. Maybe the universe bounced, it was contracting before, hit a minimum size, and bounced into expansion. Loop quantum gravity suggests this might happen. Another idea: maybe the universe emerged from nothing through a quantum process. But nothing in quantum mechanics isn't really nothing. It's filled with quantum fields and fluctuations. All these ideas are speculative. We don't have a complete theory describing the universe's origin. We don't know what happened at the Big Bang singularity, or whether there even was one. The question of what happened at the Big Bang remains one of the deepest mysteries in physics. We know the universe had a beginning. We know it was once incredibly hot and dense. But the very first moment is hidden behind a wall of ignorance. We need a quantum theory of gravity to go further. The third question: do black holes destroy information? In quantum mechanics, information is sacred. It can be scrambled, hidden, spread out, but never destroyed. This is called unitarity. If you knew the quantum state of every particle perfectly, you could reconstruct the past or predict the future. Information is conserved. But black holes seem to violate this. Imagine you write a book and throw it into a black hole. The book contains information. It crosses the event horizon and falls toward the singularity. From outside, the black hole gained mass, but you can't tell what fell in. A book, a rock, a star, the black hole looks identical. John Wheeler said black holes have no hair, they have no features distinguishing what went into them. If black holes lasted forever, the information might be locked inside. But Hawking showed black holes evaporate. Near the event horizon, quantum fluctuations create particle pairs. One falls in, one escapes. The escaping particle looks like radiation. The black hole loses mass. Over immense time, the black hole evaporates completely. The radiation is thermal random. It carries no information about what fell in. This means the book's information is destroyed. Quantum mechanics says this is impossible. General relativity says it's inevitable. For decades, physicists debated this. Hawking initially argued information really is destroyed. Others argued it must be preserved somehow. One key insight came from the holographic principle. The information might be encoded on the event horizon, not inside. The area of the horizon is proportional to the black hole's entropy. This led to the holographic principle. All information in a volume can be encoded on its boundary. The three-dimensional universe might emerge from two-dimensional information. In recent years, there's been progress. Physicists introduced quantum extremal surfaces and islands. When calculating the entropy of Hawking radiation, you need to include contributions from a region inside the black hole, an island that's entangled with the radiation. As the black hole evaporates, the island grows until it encompasses the entire interior. At that point, the radiation carries all the information is preserved. This produces the page curve entropy initially rises, then falls back to zero as the black hole disappears. Is the paradox fully solved? Most physicists think we're close. The island calculation works in simplified models, not yet proven for realistic black holes. But the resolution emerging is stranger than the problem. Information might be preserved through entanglement between the inside and outside. Space and time might be woven from entanglement. Black holes might be cosmic hard drives, storing everything in ways we're only beginning to understand. So we've named the three mysteries. We've walked to the edge where physics breaks down. Now the question is, why does this matter? Let me tell you why. First, understanding what space-time is would complete the picture of reality physics has been building for centuries. Right now we have two great theories. General relativity describes gravity and large-scale structure. Quantum mechanics describes particles and forces at small scales. Both have been tested countless times and never failed. But they can't both be right in their current forms because they contradict each other. General relativity treats space-time as smooth. Quantum mechanics says things are discrete. General relativity is deterministic. Quantum mechanics is probabilistic. A quantum theory of gravity would unify these pillars. It would give us a single framework for understanding the universe at all scales. It would be the culmination of a quest going on since the early 20th century. And history suggests major unifications lead to technological revolutions. When Maxwell unified electricity and magnetism, it led to radio, television, telecommunications, all modern electronics. When quantum mechanics was developed, it led to semiconductors, transistors, lasers, computers. A quantum theory of gravity could lead to technologies we can't imagine. If space-time is quantized, maybe we could manipulate it. Maybe we could create artificial gravity or control time's flow. If wormholes can exist and be stabilized, maybe we could use them for travel. These are wild speculations. Most physicists think it's probably not possible, but we don't know. Understanding fundamental physics often leads to applications no one predicted. More importantly, understanding space-time would answer some of humanity's deepest questions. Where did the universe come from? What happened before the Big Bang? Will the universe end? What happens inside a black hole? Why does time flow forward? Why 3 dimensions of space and 1 of time? These questions have fascinated humans for thousands of years. Every culture has origin myths. Every religion has grappled with time and existence. Philosophers have debated whether time is real or illusory, whether the universe had a beginning or always existed. For most of history, these were philosophy and religion. Science couldn't address them, but now we're close. We have mathematical frameworks, we have data, we have tools that might let us answer definitively. A quantum theory of gravity could tell us what happened at the Big Bang. It could describe black hole interiors. It could explain why time exists and flows forward. These aren't just scientific questions. They're existential questions about reality itself. There's also something philosophically profound about the possibility that space-time might not be fundamental. We experience space and time as the stage where everything happens. They seem like the most basic features of reality. The idea that they might be emergent challenges our deepest intuitions. It's similar to how solid matter is mostly empty space. When you touch a table, it feels solid. But atoms are mostly empty space, with tiny nuclei and electrons. Solidity is emergent, arising from electromagnetic forces. The table isn't fundamentally solid. If space-time is emergent, then distance and duration might be illusions in the same way. At the deepest level, there might not be any space or time. Just quantum information, correlations between quantum bits. Space and time emerge from the pattern of those correlations. This would be a radical shift in how we think about reality. This raises fascinating questions about time travel. If space-time is a fabric that can be curved, can it be curved so much it loops back on itself? Einstein's equations do allow closed time-like curves, paths through space-time that loop back in time. These solutions describe rotating black holes and certain wormhole configurations, but closed time-like curves create paradoxes. The grandfather paradox. If you travel back and prevent your grandfather from meeting your grandmother, you'd never be born. But if you're never born, you can't travel back. It's a logical contradiction. Some physicists propose ways around this. Maybe the universe conspires to prevent paradoxes. Events arrange themselves so attempts to change the past fail. Maybe time travel creates parallel timelines. When you travel to the past, you create a new branch. Your grandparents don't meet in this timeline, but you came from the original timeline. Or maybe time travel to the past is simply impossible. Stephen Hawking proposed a chronology protection conjecture. The laws conspire to prevent closed time-like curves from forming. We don't know which is correct. We don't have a complete quantum gravity theory to tell us. But the fact that Einstein's equations allow closed time-like curves suggests space-time is stranger than we imagine. Understanding this could change not just physics, but how we think about existence itself. There's also the search for life elsewhere. If we understand space-time better, if we know whether wormholes or warp drives are possible, it changes what we expect for civilization's future. If faster-than-light travel is impossible, civilizations are confined to their home systems or a few nearby stars. The universe would be full of isolated civilizations. But if shortcuts through space-time are possible, the galaxy could be connected. Civilizations could meet, communicate, trade ideas. Understanding space-time at the deepest level would tell us whether these possibilities exist or whether we're forever limited by light speed. And finally, there's the simple beauty of understanding. Humans have always looked up and wondered. We've built observatories, telescopes, particle accelerators, gravitational wave detectors to understand the universe. We've sent probes to other planets. We've photographed black holes. We've detected the cosmic microwave background. All of this is driven by curiosity. The mystery of space-time is one of the last great frontiers. It's where our two best theories collide. It's the doorway to understanding the beginning, the fate of matter in black holes, possibly the nature of reality itself. Solving it would be one of the greatest intellectual achievements in human history, comparable to Newton's laws, Darwin's evolution, the discovery of DNA. We're living in a special time. We're the first generation with tools to probe these questions seriously. We have gravitational wave detectors measuring ripples in space-time, telescopes photographing black holes, particle accelerators creating conditions like the early universe. mathematical frameworks like string theory and loop quantum gravity, we might be close to a breakthrough, or we might be decades or centuries away. Science doesn't progress on a schedule. Sometimes the breakthrough comes quickly. Sometimes it takes generations. But the fact that we're asking these questions, that we're seriously trying to understand the fundamental nature of space and time, is itself remarkable. We're pushing the boundaries of human knowledge. We're trying to understand the universe at its deepest level. And even if we don't solve the mystery in our lifetimes, the journey itself is worthwhile. Now, I want to share with you some practices, some ways you can take these ideas and let them change how you see the world. Because this isn't just about physics. It's about how you navigate uncertainty, how you hold complexity, how you ask better questions. The first practice is this: embrace uncertainty as a feature, not a bug. We live in a culture that treats "I don't know" as weakness. In school, you're punished for it. You lose points, you get marked down. In the workplace, leaders are expected to always have answers. Politicians who admit uncertainty are called weak or indecisive. We're trained from childhood to fake comprehension, to nod along even when we're lost, to pretend we understand things we don't. But science's greatest strength is its willingness to say, "I don't know yet." The space-time mystery is a perfect example. We've used Einstein's equations to build GPS satellites. We've detected gravitational waves. We've photographed black holes. Technologies worth billions of dollars rest on these equations, and physicists openly admit, we don't know what space-time fundamentally is. That's not weakness. That's honesty. That's wisdom. So here's the practice. Next time you encounter something you don't understand, whether at work, in a relationship, while learning something new, pause before the instinct to fake comprehension or feel shame. Just pause, take a breath, and ask yourself 3 questions. What do I actually know about this? What don't I know? Where's the edge of my understanding? Then write it down, make 3 columns. 1 for what I'm certain about, 1 for what confuses me, 1 for what I'd need to learn next. This is what physicists do. It's called epistemic humility, knowing the limits of your knowledge and being comfortable there. And it's a superpower, because comfort with uncertainty is the prerequisite for curiosity. If you can't admit gaps, you can't fill them. If you can't sit with not knowing, you can't learn. The most creative breakthroughs in history happened at edges, where knowledge meets mystery. Einstein didn't revolutionize physics by memorizing what everyone already knew. He revolutionized it by being willing to say, "I don't understand how light works," and sitting with that confusion until a new answer emerged. You can do this in your life. That project at work you don't fully understand? Instead of nodding along in meetings, ask, "Can you help me understand why we're approaching it this way?" That relationship dynamic that confuses you, instead of pretending it makes sense, say, "I'm noticing this pattern between us and I don't understand it yet. Can we explore it together?" Admitting you don't know creates space for discovery. Faking knowledge closes that space. The second practice, notice the invisible. Space-time is invisible, but its effects are everywhere. Most of reality operates below the threshold of our perception. Cultural norms shape your behavior invisibly. Emotional patterns run in the background. Economic systems, power structures, evolutionary instincts, all invisible forces shaping your experience. Training yourself to notice these invisible structures is a muscle you can build, and physics gives you a way to practice. Here's how. Next time you use GPS, pause for 5 seconds, just 5 seconds, and acknowledge to yourself, this works because satellites account for time running faster in orbit. Time is not absolute. Gravity affects clocks. This device in your hand is correcting for the curvature of space-time every single second to tell you where you are. You're not just using technology, you're using relativity. Einstein's equations are running in the background, invisible but essential. Look at anything gold, a ring, a necklace, a coin. Remind yourself, that color exists because of relativity. Electrons in gold atoms are moving so fast that space-time effects matter. The color yellow is a consequence of special relativity. Without it, gold would look like silver. When you see the moon, remember, the light hitting your eyes took 1.3 seconds to travel from the moon to you. You're seeing the past. You're always seeing the past. Light from the sun takes 8 minutes to reach you. Light from distant stars takes years or centuries or millions of years. There's no universal now. When you look at the night sky, you're looking at a time machine, seeing different moments in cosmic history simultaneously. Watch water swirl down a drain. Notice the vortex forming. It's an emergent pattern. The vortex isn't made of special vortex material. It's water molecules moving in a coordinated way that creates something new, something that didn't exist in any individual molecule. Temperature works the same way. It's not a property of individual atoms. It's a statistical description of their collective motion. Space-time might be like this, an emergent pattern from something deeper, something we can't perceive directly, but whose effects shape everything. Why does this matter? Because most of what's real is hidden from direct perception. Learning to see invisible structures, whether space-time, cultural assumptions, emotional dynamics, systemic forces, is how you develop wisdom. Physics trains you to look past surfaces, to ask, what's really happening here? This skill transfers to everything. You start noticing the invisible forces shaping your relationships, the unspoken rules governing your workplace, the assumptions you inherited without questioning, the patterns you repeat without awareness. Once you start seeing the invisible, you can't unsee it, and that's when real change becomes possible. The third practice, ask better questions. The quality of your life is determined by the quality of your questions. Most people spend their lives answering the wrong questions. They ask, how do I get rich? Instead of what does abundance mean to me? They ask, how do I make them like me? Instead of what kind of connection am I actually seeking? They ask, how do I solve this? Without first asking, what's the actual problem here? Physicists didn't solve spacetime's mysteries because they were smarter than everyone else. They solved them because they asked better questions. Einstein didn't ask, how does gravity work? Everyone was asking that. He asked, what would it look like to ride alongside a beam of light? That question, weird, playful, specific, unlocked special relativity. He asked, what if falling and floating are the same thing? That unlocked general relativity. The three unsolved mysteries we've explored exist because physicists learned to ask precise, answerable questions. What is space-time made of? Not, what is reality? Which is too vague. What happened at t=0? Not, where did everything come from, which mixes physics with metaphysics? Is information conserved in black hole evaporation? Not, what are black holes really? Good questions have three qualities. They're specific, they're answerable in principle, and they open up new territory rather than closing it down. Here's the practice. Keep a questions journal. Every day, write down one genuine question, not rhetorical, not a complaint disguised as a question, but a real inquiry where you don't know the answer. Bad question, why is my job so frustrating? That's not actually a question, it's a statement of dissatisfaction. Better question, what need isn't being met by my current work? What would fulfillment look like? What's the smallest change that would matter? Bad question, why can't I ever focus? Again, that's self-criticism wearing a question mark. Better question, under what conditions do I focus easily? What's different about those times? What's one environmental change I could test? Notice how better questions open possibilities. They invite exploration. They assume answers exist. You just haven't found them yet. Your life has mysteries too. Things you don't understand about yourself, your relationships, your patterns. Most people never examine these mysteries. They just live with vague dissatisfaction. But if you start asking better questions, the mysteries begin to reveal themselves. Why do I always choose unavailable partners? Becomes, What am I actually afraid of in available relationships? Why do I procrastinate? Becomes, what makes me feel safe enough to start? Why can't I change? Becomes, what would need to be true for change to feel less threatening? Better questions transform suffering into curiosity, and curiosity is the antidote to despair. The fourth practice, hold paradox without resolving it. Space-time is full of paradoxes that are both true simultaneously. Time is relative and clocks measure it consistently. Space is empty and it's something that bends. Light is a wave and a particle. Black holes destroy information and information is conserved. Most people try to collapse paradoxes into single answers. They pick a side. They need things to be one way or the other. But physicists have learned to hold both sides simultaneously until a deeper framework emerges. Newton's laws and Maxwell's electromagnetism seemed incompatible, one for matter, one for light, using different principles. People argued about which was more fundamental, but they were both right. They're both approximations of special relativity, which reconciles them at a deeper level. Quantum mechanics and general relativity seem incompatible now. People argue about which needs to change, but probably they're both right, both approximations of something deeper we haven't discovered yet. Here's the practice. Identify a paradox in your life, something where two contradictory things seem true. Write them both down. I want deep connection with people, and I need extensive time alone. I'm confident in my abilities, and I frequently feel like an imposter. I love my partner, and they drive me crazy. I value stability, and I crave change. Most people try to resolve these by choosing one side. I guess I'm just an introvert, connection isn't for me. Or, I guess I'm not confident, the imposter feeling is the truth. But that's collapsing the paradox prematurely. Instead, sit with both statements. Write them down, look at them, ask, what would it look like if both were true? What framework would allow that? Often the paradox dissolves not because one side was wrong, but because you were operating in a limited framework. Connection and solitude can coexist when you realize relationships aren't all or nothing. You can have deep connection and still honor your need for alone time. Competence and imposter feelings coexist when you understand that expertise is contextual and learning never ends. You can be genuinely skilled while still feeling like a beginner in new situations. The contradictions you feel aren't problems to fix. They're signs you're outgrowing your current framework. Hold them. Let them sit. Let them transform you. This is how growth happens. Not by resolving contradictions, but by developing a larger perspective that can hold them both. A child can't understand how their parent can be both angry at them and love them simultaneously. It seems impossible. An adult understands that love and frustration coexist easily. The child didn't need to resolve the paradox. They needed to grow into a framework large enough to hold it. You have paradoxes you'll grow into too. Parts of yourself that seem contradictory now will make perfect sense 10 years from now when you've developed a richer understanding of who you are. So hold the paradoxes. Don't collapse them prematurely. Let them teach you. Now I want to bring us toward a close. We've traveled a long way tonight. We started with a question most educators won't ask. What does it feel like to not know? And we spent 2 hours sitting with one of science's greatest mysteries, space-time, this idea we use every day but don't fundamentally understand. We've walked through Einstein's revolution, through his insight that space and time are flexible, that gravity is the curvature of space-time itself. We've seen how his equations predicted black holes and gravitational waves decades before we found them. We've watched his theory succeed spectacularly, while simultaneously predicting places where it fails, singularities where the math breaks down, and infinity appears like a warning sign saying, beyond this point, physics doesn't work. We've explored the three great unsolved mysteries. What is space-time made of? We don't know. It might be loops of quantum geometry. It might be vibrating strings in higher dimensions. It might be an emergent property of quantum entanglement, or it might be something we haven't imagined yet. What happened at the Big Bang? We don't know the equations point to a singularity, but break down before they can tell us what actually occurred at t = 0. Do black holes destroy information? We're getting close to an answer, and it involves ideas so strange they challenge everything we think we know about reality, information preserved through quantum islands, space-time woven from entanglement, the universe as a hologram. And we've connected all of this to your life, to GPS satellites correcting for time dilation, to the color of gold in your jewelry, to gravitational waves detected by instruments sensitive enough to measure changes smaller than a proton, to photographs of black holes 55 million light-years away, showing light bent by extreme space-time curvature. But more than that, we've sat together with uncertainty. We've practiced acknowledging what we don't know. We've looked at the invisible forces shaping reality. We've asked better questions. We've held paradoxes without collapsing them prematurely. And here's what I want you to take from this. You don't need to understand everything to appreciate it. You don't need answers to ask good questions. Mystery is not the absence of knowledge, it's the presence of something greater, waiting to be understood. Space-time is real. We've measured it, we've photographed it, we've used it to navigate, we've detected waves moving through it, and we don't know what it fundamentally is. Both of these facts are true, and both are beautiful. The universe is not obligated to make sense to you on your timeline, but it is knowable. Every mystery we've ever confronted, from the motion of planets to the origin of species to the structure of DNA, eventually yielded to curiosity, rigor, and patience. This one will too. Maybe not in our lifetimes, maybe not for 100 years, but the question is alive. The inquiry is open, and somewhere, right now, there's a physicist working late in their office, or a graduate student staring at equations on a whiteboard, or a theorist having a sudden insight while walking through a park, who's getting closer to the answer. And the fact that you've spent 2 hours tonight sitting with these ideas means you're part of it. You're part of the human project of understanding the cosmos. You're standing in a long line of people who've looked up at the sky and wondered, who've asked, what is this all made of? And refused to accept, we'll never know, as an answer. Here's the mantra I want you to carry with you. I don't have to know everything to know something matters. I don't have to solve every mystery to honor the questions. Uncertainty isn't emptiness, it's invitation. The map has blank spaces. That's where the adventure begins. You're not lost because you don't understand space-time. You're exactly where every honest person is, at the edge of what's known, looking out at what isn't, with curiosity instead of fear. And in your own life, with your own questions, your own uncertainties, your own mysteries, you can do the same thing physicists do with space-time. You can measure what's measurable. You can be honest about what isn't. You can hold paradoxes. You can ask better questions. You can sit with not knowing while still moving forward. Because here's the deepest truth. Growth doesn't require certainty. It requires honesty about uncertainty. Einstein revolutionized physics, not because he had all the answers, but because he was willing to ask, what if everything we think we know is wrong? And follow that question wherever it led. Even if it led to conclusions that seemed impossible. Even if it meant time wasn't absolute, and space could curve, and the universe was stranger than anyone imagined. You can do this too, in your work, in your relationships, in your understanding of yourself. You can question the assumptions you've inherited. You can look for the invisible forces shaping your experience. You can acknowledge what you don't understand and let that acknowledgement be the beginning of discovery rather than the end of hope. The physicists working on quantum gravity right now don't know if they'll solve it. They don't know if loop quantum gravity or string theory or something entirely different will turn out to be right. They don't know if the answer will come in their lifetimes. But they keep working because the question matters, because understanding matters, because pushing the boundaries of what's knowable is how humanity has always moved forward. And your questions matter too. The things you don't understand about yourself, about your life, about what makes you who you are, those aren't defects, they're invitations. They're the blank spaces on your personal map where discovery happens. So I want to leave you with this. The next time you feel uncertain, the next time you encounter something you don't understand, the next time you're tempted to pretend You know something you don't remember? Spacetime. Remember that we've built entire technologies on equations we don't fully comprehend. Remember that the smartest people in physics openly admit the limits of their knowledge. Remember that mystery isn't failure, it's frontier. And then ask yourself, what would happen if I treated my uncertainty the way physicists treat theirs? With honesty, with curiosity, with the understanding that not knowing yet is different from never knowing. What would happen if I stopped pretending I have it all figured out and started asking better questions? What would happen if I noticed the invisible forces shaping my life, the way physicists notice the invisible curvature of space-time? What would happen if I held my contradictions without collapsing them, trusting that a larger framework will eventually emerge? What would happen if I treated mystery as invitation instead of obstacle? I think you'd discover something remarkable. I think you'd discover that not having all the answers doesn't make you lost, it makes you human. And it makes you part of the greatest adventure there is, the attempt to understand. So if this journey tonight resonated with you, if something shifted in how you see space or time or uncertainty itself, I'd love to hear about it. Leave a comment. Tell me which of the three mysteries fascinates you most. Or share a paradox from your own life that you're learning to hold without resolving. Tell me about a question you're sitting with, or an invisible force you've started to notice, or a moment when admitting "I don't know" opened up possibility instead of closing it down. And if you want more explorations like this, deep dives into ideas that make the universe strange and beautiful and mysterious and knowable all at once, I invite you to subscribe, not because I need the numbers, but because every person who joins means we're building something. A community of people who aren't afraid of hard questions, who can sit with uncertainty, who understand that the most interesting place to be is at the edge where knowledge meets mystery. Every like, every share, every conversation started by these videos helps more people find this kind of content. It helps us create a culture where "I don't know" is the beginning of inquiry, not the end of credibility, where mystery is honored instead of feared, where curiosity is valued more than false certainty. Thank you for being here tonight. Thank you for your willingness to sit with these questions for 2 hours. Thank you for not needing easy answers. Thank you for your curiosity, your openness, your capacity to wonder. The universe is full of mysteries. Space-time is just one of them. But it might be the most important one, because understanding what space and time really are might unlock everything else. It might reveal what happened at the beginning. It might show us how to unify quantum mechanics and gravity. It might open up technologies we can't imagine. It might answer questions we didn't even know how to ask. Or it might reveal deeper mysteries we never suspected were there. And that would be beautiful too, because the point isn't to eliminate mystery. The point is to transform it from something that paralyzes us into something that pulls us forward. Einstein spent the last 30 years of his life searching for a unified field theory. He never found it. He died with the work unfinished. And you might think that's tragic, but I think it's beautiful. He spent 3 decades pursuing a question that mattered, knowing he might never solve it, because the pursuit itself gave his life meaning. The answer matters, but the asking matters more. So keep asking, keep wondering, keep sitting with what you don't understand while still showing up to understand a little more. The map has blank spaces. And that, my friend, is exactly where the adventure begins. Good night.